Section 5.1 Eigenvectors and Eigenvalues. In this chapter, we're going to look at square n by n matrices and think of the transformation from x to a times x as moving vectors around in our Rn space. So sometimes for certain matrices and certain vectors, the action is simple. In this example, we're going to look at our matrix A, given here, it's a 2 by 2, and a vector v. So if we multiply A times our vector v, remember that we're going to go across and down. And so when we do that, our first entry will be 4, and our second entry will be 2. And if you take a look at the relationship here, then you can see that that is exactly double the vector v. So we've multiplied v by 2. So for any multiple of v, we have this relationship happening. If we multiply v by k, then when I multiply that by my matrix A, remembering our rules of matrix multiplication, I can pull that scalar out, and we know that A times v from up here was simply 2v. So I've got my scalar times 2v, which is 2 times kv if I move it around again. So any multiple of v maps into twice itself. So let's look at a couple of definitions. An eigenvector of an n by n matrix is a non-zero vector x such that when I multiply A times my vector x, my matrix A times x, then I have what we call lambda x for some scalar lambda. So in our previous example, what happened when we multiplied our vector v by our matrix A, we ended up with 2v. So then 2 would be what we're talking about when we're talking about lambda. 2 would be our scalar. So the eigenvector is the vector x, and then our scalar lambda is called an eigenvalue of A if there is a non-trivial solution x of our solution A times x equals lambda times x. Such a vector x is called an eigenvector corresponding to the eigenvalue lambda. Take note that eigenvectors are always non-zero vectors, but eigenvalues can be positive, negative, or 0. So let's look at an example. Here we've got a matrix A and two vectors u and v. And we want to check and see, are the vectors u and v eigenvectors of A? So we're going to look at multiplying each vector by our matrix A. So first we'll multiply A times u. So here I've written my matrix A and my vector u, and remember, to multiply you're just going to go across and then down, so we'll end up with our vector negative 2, which is equivalent to negative 2 times u. So since I could write that as a scalar times my vector u, then I know that u is an eigenvector. Now we're going to look at A times our vector v. So here I have my matrix A multiplied by the vector v, and when we multiply across and down, we will end up with the vector negative 2, 6. And that is not equal to any kind of scalar multiple of my vector v. So then v is not an eigenvector. So we need to ask ourselves the question, how can we determine if a given number lambda is an eigenvalue for A? So we know we've got this set up here, this equation, ax equals lambda times x, and we're trying to see if a given number will satisfy that equation. So if that's true, then it is the same as taking ax and putting it equal to lambda times the identity sub n times x. So basically the identity is just like multiplying by 1 and multiplying that by our vector, we still get our vector x. So we haven't changed the equation. However, now I'm going to subtract this expression so that I have ax then minus lambda I x. And we don't need to specify that it's I sub n anymore. And that is equal to 0. So if I factor out, in a sense, my vector x, and it's being multiplied on the right, then I have a minus lambda I on the left times x equals 0. So we know then that lambda is an eigenvalue if and only if my equation that we just came up with has non-trivial solutions. The set of all solutions to our equation a minus lambda I times x equals 0 is the null space of a minus lambda I. So this set is a subspace of Rn called the eigenspace of A corresponding to lambda. In this example, we want to show that 4 is an eigenvalue of our matrix A, and we want to find the corresponding eigenvectors. So then 4 is an eigenvalue of A if and only if our equation ax equal 4x has a non-trivial solution. And we saw in the previous slide how we can solve this, and we end up with a minus 4I times x equals 0. So we're checking to see if we have a non-trivial solution to that. So first let's look at what a minus 4I will be. So here's our matrix A, and remember 4I, we're simply going to multiply the identity times 4. So we'll have 1's on the diagonal multiplied by 4. So we'll get 4's on the diagonal and 0's everywhere else. So what we want to do is we want to subtract those two matrices from each other. And we will get this matrix here. So now I want to solve where I set up an augmented matrix with a minus 4I as the first part and then zeros. So we'll have this matrix here, and we're going to row reduce it, and we'll get this matrix here. So if we set up our general solution, we have x1 is equal to negative 1/2 x2, and x2 is free. So we'll write it out with x2 pulled out, and we'll have negative 1/2 and 1. So each vector of the form x2 times negative 1/2 1 is an eigenvector corresponding to our eigenvalue lambda equal 4. So we've shown that we have a non-trivial solution to our equation, so we can see then that 4 is an eigenvalue of our matrix A. And if we look at it visually here, we can see that here we've graphed a vector negative 1/2 and 1. And then up here we would have 4 times that. So we have the vector negative 2, 4. So it gives us a visual of what our solutions are looking like. In this example, we're going to let A be this matrix here. It's a 3 by 3. And an eigenvalue of A, we're told, is lambda equal 2. So what we want to do is find a basis for the corresponding eigenspace. And remember that the eigenspace is the set of all solutions to our equation, which is the null space of our A minus lambda I. So we're trying to find a basis for that eigenspace, which is essentially a basis for a null space. And remember, when we were doing that, we had to set up a matrix, row reduce it, and find the general solution. So we're going to look at A minus 2I. So here we have our matrix A, and we're subtracting then the identity matrix multiplied by 2, and we get this matrix here. So when I look at my equation A minus 2I times x equals 0, then I'm wanting to row reduce our matrix where we set it up with A minus 2I and then a column of zeros. So we have this matrix set up here, and we're going to row reduce it. And we'll produce this matrix here. So let's look at the general solution. We'll solve it, and we see we have x1 equals x2 plus x3. x2 is free and x3 is also free. So we'll pull out x2 first, and we have 1, 1, 0, plus x3 then times 1, 0, 1. So then those two vectors form a basis for our eigenspace. So then a basis for the eigenspace corresponding to our eigenvalue lambda equal 2 is the set containing those two vectors we just found. In this example, we want to suppose lambda is an eigenvalue of a, and we want to determine an eigenvalue of a squared and a to the third. In general, then, we're going to look at what an eigenvalue of a to the n power would be. So, since lambda, we're told, is an eigenvalue of a, then we know that there is a non-zero vector x such that a times x is equal to lambda times x. So I'm going to take my equation and I'm going to multiply on the left by a on both sides of our equation. Then over here on the left side we have a squared times x. And then what we can do here on the right side, since lambda is a scalar, I can move where it's located. So I'll have lambda times ax. But we just said that ax is lambda times x, so then I have that a squared x is equal to lambda then times lambda x. Well, now this is lambda squared times x. So I have found that a squared times my vector x is equal to lambda squared times x. So therefore lambda squared is an eigenvalue of a squared. Let's keep doing what we were doing here and take this equation now that we have here, and we're going to multiply on the left by a in that equation as well. And this is because we want to look at a cubed. So over here on the left side we have a cubed now times x equals, and remember that we can reorder this, so I can move lambda squared to the front and multiply it by just ax now. And we know that ax is still then lambda x now times lambda squared. And so then on my right side I have lambda cubed times x is equal to a cubed x. So therefore lambda cubed is an eigenvalue of a cubed. So we're going to make a generalization from both of these and say that in general lambda to the nth power is an eigenvalue of a to the nth power, since we could continue on in this fashion infinitely. So now let's ask the question, if I'm given a matrix, how do we find the eigenvalues? And in answer to that, we're going to find out in the next section. So we don't know how to do that just yet. But we can look at the following. The first is Theorem 1. The eigenvalues of a triangular matrix are the entries on its main diagonal. So now we want to ask, what happens if 0 is an eigenvalue? If we've got a triangular matrix, I mean we either have zeros in the upper triangle or zeros in the lower triangle, we could have a 0 along our diagonal, and so what do we do if that happens? What that means then is that ax is equal to 0x, which is equal to 0. So this means that the equation ax equals 0 has a non-trivial solution, because x can be anything, and a is then not invertible. If we remember from the invertible matrix theorem, A is an invertible matrix if and only if then the equation ax equals 0 has only the trivial solutions. So since we have a non-trivial solution, we know A cannot be invertible. So then we can now make an addition to the invertible matrix theorem and say this S, the number 0, is not an eigenvalue of A if the matrix is invertible. So remember that we can still have an eigenvalue of 0, but if that happens, then our matrix is not invertible. So all this is saying is in order for it to be invertible, we know 0 could not have been an eigenvalue. And then the last thing we're going to look at is theorem 2, which says that if I have vectors v1 through vr that are eigenvectors and they correspond to distinct eigenvalues, lambda 1 through lambda r, of an n by n square matrix A, then the set containing those vectors, v1 through vr, is linearly independent.